Yes.
Okay, so welcome to this new initiative of our department, the alumni seminar or lecture series, where we will have our former students to come and maybe spend an hour virtually with us. So the first speaker in this series is Dr. Debdatta Sinha Roy. So Debdatta is a alumni of MS-09 batch, if I remember it correctly. So in Debdatta's batch, I think there were 29 students in mathematics. Yeah, but so this is one of the things that we are working now, because nowadays the number of students who are coming to mathematics is comparatively lesser than the time when Debdatta used to be a student. And when Debdatta and Keshav joined IISERM-Mohali, essentially there was nothing. It was, kind of new campus, lots of problems, but they survived and they are now well settled in their life. That's great. So Debdatta went to University of Maryland for doing a PhD. So he did his PhD in business administration at University of Maryland. And after that, right now he is working in Oracle. So I don't know your designation in Oracle. Can you remind me the designation?
I'm a senior research scientist.
Okay, so Debdatta is a senior research scientist in Oracle, and he is now staying in Boston. And today he will be giving the lecture on the topic. Let me just recall the topic also. I am the same. You can see a bit. Yeah. But Debdatta and I are in touch since he left here. And when I visited University of Maryland, I still remember the hospitality that you provided me. And I really like that cafe. We went together to have some drinks and those chicken snacks, right? That was really nice. I really enjoyed that. And I thought we will meet again and he will take me a tour by your car, but unfortunately due to the pandemic, it never happened. So today, Debdatta will be speaking on data-driven optimization and statistical modeling to improve meter reading for utility companies, which looks a very interesting topic with real life applications. So Debdatta, you can start your talk. And I hope you have already started the recording also.
Yes.
Yeah, okay, great.
Thank you, sir, for the nice welcome and invitation to the alumni seminar series. Thank you for the whole math department for putting together this. This is a great way for the alumni to contribute and also motivate the current students. Okay, with that, I will start. And please feel free to ask questions as we go. Let's make it interactive. I don't want to be just one-sided. Yeah, I hope everyone can see my screen. If someone can confirm.
Yeah, I can see.
Okay,
no problem.
Okay, thank you. Yeah. Yes, so let's get started. Little details like about my background. So I joined IISERM-Mohali in 2009, graduated in 2014. So I was the third batch of IISERM-Mohali. Yeah, as Krishnendu sir mentioned, it was like the institute was still building. I spent the first 3 semesters in Sector 26, the transit campus. And then from semester 4, I spent in the main campus. In 2014, I went to the Smith School of Business, University of Maryland, to do a PhD in operations research. In 2019, I graduated. I then moved to Staples in Boston, Greater Boston area, where I worked as a research scientist in the supply chain, logistics, transportation domain. And recently, like a few months back, I moved to Oracle, also in the Greater Boston area. Here I am in the data science R&D team as a senior research scientist. Well, on my, so as a researcher, I work on optimization, machine learning, data science, and on the business domain, I build algorithms for supply chain, logistics, transportation, retail science. And some more like details about my like academic tree and all. So the right side is my academic tree. So George Danzig, he is one of the, like, he is known as the father of modern linear optimization. He is the inventor of the simplex algorithm. So, and my advisor, Bruce Golden, so he is one of the pioneers of vehicle routing, one of the branches of modern optimization. Vehicle routing is used all around us, Google Maps routing, and all sorts of routing stuff that goes around. So if someone is hiring a Uber, someone is getting food delivery, it's all vehicle routing. And I get my ADOS number 3 from the tree on the left hand side. So that's how, yeah, so Daniel Kleitman co-authored with ADOS. My advisor had a co-author with Daniel Kleitman, and yeah, that's me. And I dedicate this talk to Professor Pasi because yeah, his presence was like, his contributions were immense to the ISER Mohali community, and he played a very important role to our institute building. And I have some very personal memories with Pasi sir. So I did my first summer project in 2010 summers with Pasi sir. I also did my final year project 2013 to 2014 with Pasi sir, and he helped me a lot kind of with my research, with getting the confidence, like starting with mathematical proofs. um, the- so I the first summer I remember I walked into his office. It was the first summer project. He asked, what do you want to learn? And I said, I am not very comfortable with proofs. And he said, okay, go to the board and prove something. And I said, well, I'm scared. I need to learn. And he said, that's how you learn. Just go to the board and start doing it in front of me. So yeah, his contributions are immense to my life, to all the initial batches who have interacted with Pasi sir. Okay, so let's get started with the topic. And yeah, please stop me if there are any questions. So let's start with the introduction to the problem. Um, Meter reading problem is a very real world practical problem. So it's like reading meters in our houses. So this is at the intersection of statistical modeling, route optimization, and big data. So utility companies need to read electric, gas, and water meters of residential and commercial customers on a regular basis, and it is done automatically using RFID, radio frequency identification technology. Um, so this AMR systems, the automatic meter reading systems, consists of two components. One, RFID tags that are connected to the meters in our houses, and then vehicle mounted reading devices, which are the receivers that receive the signals. So this technology might not be that efficient in high-rise apartment buildings, but in like in countries like US, where most of the US is like 1-2 storied houses spaced apart, this works very well. So the vehicle drives by with a receiver, and the houses with the meters with the RFID tags, they send out the signals, and the vehicles pick up the signals while driving by, and your meter is read. So this automatic way of reading meters actually transforms a standard vehicle routing problem to a close enough vehicle routing problem. And I'll explain, like I'll illustrate how it transforms. And this transformation actually helps because it reduces the total route length. So this is a typical neighborhood. We see streets, the green dots are locations of various meters. Basically, those are houses in which the meters are installed. This is a standard VRP. So a driver needs to travel through all the street segments along which the houses or the meters are located. And the driver will kind of park their vehicle and get down and manually read the meter. But this is like just a standard VRP. You have to travel through all the street segments along which the meters are located. And this is a close enough VRP. So if the meters don't have to be read manually, if they have a radius, if the signals have a radius of say 500 feet, yeah, pardon me, with the CGS system in the US, we're just used to using or the same CGS systems. So if the meters have a uniform radius of 500 feet, then you don't have to always travel across all these street segments. You can skip certain street segments. Suppose the vehicle is driving by here, but it is able to pick up signals from these meters. And if the vehicle is driving here, then it is also able to pick up signals from here. So this is like a closed enough vehicle routing problem, and it reduces the total route length immensely. But this is also even a harder problem than the VRP. A VRP problem is an NP hard problem to start with. With a close enough VRP, it is even harder, because not only you have to design the route, but you have to kind of choose. So you have to again make a choice among set of all possible choices. Yeah. Okay. So, however, there are various issues with this RFID technology. It's not all good as it sounds. So the signal transmission is discontinuous. It doesn't happen continuously because of energy conservation. Then there are various obstacles or like stochasticity going on in the environment around us. Weather conditions play an important role. Cloudy overcast conditions is not good for the signals to travel far. Then there are surrounding obstacles. If there's a big building or something between the meter and the street segment, then the signals cannot travel. Then the battery lives of the transmitters decrease, and that affects the range. And then if there are many other RFID sources along like around a meter, that leads to signal interference and the signals die out. So on an average, utility like a typical utility company in a city has to have to read about 1.5 million meters on a monthly basis, and about 5 to 10% of the meters are missed. So when the vehicles drive by, they miss many signals because of the above mentioned situations, and so about 10% of the meters are missed. And in many kind of jurisdictions, estimated billing is not allowed. Suppose the state of Illinois says that you can only do estimated billing like once every other month. So you cannot have estimated billings consecutively across over 2 months. And so if you have already missed a meter last month and have done estimated billing for that, you have to read it this time. And so what ends up happening is the vehicle like the company has to send another vehicle at the end of the day. So these technologies, it's a passive RFID technology. So while the vehicle is driving, it doesn't know which meters the vehicle is reading or not. Only after it goes back to its office, all the data is transmitted, then only they get to know, okay, these are the meters I missed, which I should have covered today. And so they have to send back a vehicle again, like pay overtime charges to the driver, and all sorts of overhead charges. And so that's why it's a expensive affair. And so what can we do mathematically using the data available to build robust routes? So yeah, that's what we want to address. We want to address the issues with the RFID technology in the domain of meter reading by generating routes that are robust on a street network and that minimizes the number of missed reads. And we want to use the fields of statistical learning, optimization, data analytics. So yeah, the goal is to design high quality routes that are short in length and better at capturing the uncertain signals from the meters. Okay. Um, any questions with the introduction? Anything that's missing, or if the problem description not very clear, now might be the time to clarify. Okay, I'll move ahead. So let's take a look at the data that's available. So first of all, the information about the the street information is available, the shape, length, and type of streets. Then we have the location, the lat longs of the meters in a 2D plane, and then all the reading events. Basically, at every second we get the information that what all meters are covered within a span of that second while the vehicle is traveling, and obviously a unique ID of the meter that is getting covered. And this data is in GIS format, geographic information systems, a very popular like format for geographic data. And I got the data during my PhD from Route Smart Technology. It's one of the leading companies in the US East Coast that does all sorts of like routing, for example, snow cleaning, meter reading, and many other public works. So this is a sample data set. So the red lines are the street segments. The green dots is the location of the vehicle every second as the vehicle moves through its route. The blue dots are the meters that are covered by the vehicle, that were read by the vehicle while the vehicle was traveling. The yellow dots are the meters that have been missed from the vehicle's route. Um, and as expected, we can see that as we go farther away, there are more yellow dots because the signals are out of the range of the vehicle. But very close to the meter here, we can see very close to the vehicle, we can see that there are many meters that have been missed. And so this is an example of the real world stochasticity. So and we can see on the far left corner that a meter has been read that far. So yeah, how can we build routes in such a stochastic environment so that we minimize the total route length and also minimize the number of missed reads? Just some kind of idea about the real world picture of the size of the graph we are dealing with. So the number of nodes we have is 1,000. About 1,000. Number of street segments we have is about 6,000. Number of meters that I have along these street segments is about 5,000. And I have data of a route of 6 hours. The time between every signal transmission is 3 seconds. And about 337,000 read events were recorded in the route of 6,000 from those 5,000 meters. And yeah, okay. Now let's get into some real math. So there are two components to it, the optimization part and the statistical learning part. So first I'll cover the optimization part. So the problem of defining the optimal route is formulated as a two-stage IP. And the motivation is that VRP is already an NP-hard problem. This is a CE VRP, the close enough VRP, not the standard VRP, which is even harder than that. And on top of that, we are adding a lot of stochasticity. We have to account for uncertainties, probabilities. So solving the problem at one go, it's like for any real life instances within any practical time limit of few hours, it's not possible even to get a feasible solution. So we divide the problem into two stages. The first stage can be solved optimally. So even though the global framework becomes suboptimal because I'm breaking the formulation into two parts. However, this is needed for solving real life problems at scale within a reasonable time frame. So in the first stage, the utility company managers they decide numbers for each specific meter that they want to read a particular meter A with 95% likelihood. They want to read meter B with 90% likelihood. And this is very helpful for them because this way of designing of the problem, because if they have missed the meter last time and they have to read the meter in this month, they can assign a very high likelihood of 95% on that meter. Whereas if they have read a meter last month and they can do estimated billing, so they can push all those meters with a lower likelihood. And accordingly, your routes will become smaller because you don't have to do too much of effort in like reading those meters. You can miss, and that's okay. Uh, so so the stage one IP actually gives certain street segments all across the network that needs to be traversed for reading each of the meters with the pre-specified likelihood. And then the solution of stage one IP is used into a stage two integer program. And that is just basically solving a NP-hard problem, which is a rural postman problem, which basically means that given certain street segments all across the network, how do I connect that from the starting and ending location? So we call it a depot. That's where the vehicle starts its journey and it has to come back to the depot. So given certain street segments that one needs to travel as a result of the stage one IP, what you have to do in the stage two is just kind of connect the route. And that is an NP hard problem. So that is called a rural postman problem. Okay, now let's kind of dig deeper into the IP formulations. Yes. So the set I is the set of all meters. E is the set of all edges, and also or like two-way street segments, streets in which traffic can go two ways in both the directions. A is the set of arcs or one-way street segments. CJ is the cost of traversing street segment J once. Li is the pre-specified likelihood of reading meter I, as I was explaining in the last slide, that the utility company managers can feed these numbers based on what they want to do with a particular meter. Li is a fraction between 0 and 1. Xj is a decision variable. It's a binary decision variable. So xj, 0 meaning the particular street j will not be traversed, and xj1 is that particular street will be traversed once. So the stage one formulation does not allow for the vehicle to repeat a street segment. It can only be 0 or 1, but the repetition part will be covered in the stage 2. And why we don't allow it to repeat? Because of the constraint that we have, the exponent xj. I'll explain. And pij is the probability that meter I is read from street segment j at least once. So so the constraint 1 minus Pij is the probability that meter I is not read from. So 1 minus Pij is the probability that meter I is not read from street segment J. When you take a product on the left hand side across all the street segments, the left hand side of the constraint gives the overall probability of missing meter I from the full vehicle route, and that has to be less than 1 minus Li, because Li is the likelihood with which I'm planning to read meter I. And if the exponents is different, like more than 1, then this equation doesn't work out. And so that's why the stage 1 IP is only restricted to a binary decision variable. So when this is 0, basically I'm not traversing I'm not traversing street segment J. 1 minus Pij to the exponent of 0 will be 1. Basically, the probability of missing meter I from street segment J is 1, because I'm not traversing it. And if xj is 1, then the probability of missing is 1 minus Pij. And then we take the product over all these street segments. And the objective is minimizing the total cost. So Cj is the cost, Cj times xj. So this is a linear integer program. Actually, this is a linear binary integer program. And just to compare it with the traditional, the deterministic version, so the left hand side
So
integer program
may
is,
I
yeah.
interrupt for a minute? Yeah. So if I am is the in order to write this as a product, aren't we saying that somehow the uh, traversals are independent of each other if the segments are connected and so on?
We are assuming independence. Yeah,
Okay. Yeah.
that's a assumption to the formulation. That's very correct. However, if there are correlations, we will learn that while learning the PIJs using the statistical learning. So it does not, again, so it's not the optimal way of doing it, but it's the practical way of doing it, that the formulation assumes independence. However, the Pij values will be very close enough if two street segments or 2 meters are close enough and they behave similarly.
Okay.
Yeah. So this stage 1 formulation is for the stochastic version where the RFIDs are not working as planned. It's not just given by the book that 500 feet, like a constant radius of 500 feet. However, if that would have been the case, the deterministic CEVRP, then this is how the problem looks like. So again, we are minimizing the total cost, Cj times Xj, and the constraint is simple. So Aij is again a binary parameter. So Aij is 1 if meter I is covered from street segment, and there is nothing probability involved. It's a deterministic situation. So Aij is 1 if meter I is within 500 feet from at least one location in street segment J. We can think of it that way. And 0 otherwise. Basically, Aij is 1 if meter I is within the range of street J, and 0 if it's not. So what we are saying, that is summation over all the street segments Aij times Xj should be 1. That is each meter I for all I. So each meter I has to be read from at least one street segment. That's why it's greater than or equals to 1. So this is the deterministic version of the stage 1 of the CEVRP, close enough VRP. And on the left side, we have the current version based on all the stochasticity and how can we capture the probability. Now, so this equation, we can take log on both sides, and this becomes a linear IP. And just because it's a linear IP, computationally, we can prove that like for thousands of meters and street segments, we can solve this optimally within few seconds. So again, so George Danzig, his simplex algorithm does the wonders. Okay. So now let's look at the stage 2 IP. So once we get the solutions from the stage 1 IP, which is basically certain xj's are 0 and certain xj's are 1. That's what we get from the stage 1 IP, whether to traverse or not traverse certain street segments. Now, stage 2, again, we have now a overall objective function that kind of minimizes the total route length. So just remember that stage 2 needs to connect those street segments that we have obtained as a solution, and I'll illustrate it in diagrams in the next slide. And so this is all about finding the connections, starting and ending at the depot. So the first constraint makes sure that the depot is a part of the route, that the depot is connected. The second constraint is a flow conservation constraint. It makes sure that the degrees of each node is even. Either it's 0, 2, 4. Otherwise, the vehicle will reach a node, and at some point it will have no ways to leave the node. This constraint, it's called a disjoint subtour elimination constraint. Basically, there is no way without this constraint to enforce that it will be just one route. There might be small routes and those will be feasible solutions to the problem if this constraint is not there. This ensures that it will be one big route, because if the routes are small, like small other subtours, then the objective function is lower, and so the optimization, since it's a minimization problem, it will choose a solution like that over a complete route. But so with this constraint, we do away with that. This is a balanced set inequality constraint. And this is important because we are dealing with a mixed graph where we have both edges and arcs. So this says that if we look at a subset of nodes, the number of arcs coming in minus the number of arcs going out cannot be more than the number of edges kind of coming in or going out from that subset. Otherwise, again, you are stuck, because you come in and you kind of, there are more arcs to come in than to leave. Then the edges are the ones who will save your day. So yeah. And y j greater than equals to 1 are for those variables like transferring from the stage 1 IP. If xj equals to 1 was the solution to the stage 1 IP, then for those j's, yj has to be greater than equals to 1. And they can be like higher values. So this time we are allowing for repetition of street segments. And yeah, so we are saying that streets that are solution of stage 1 will be part of the solution, but they can be repeated also. And the others that were not a part of the solution of stage 1 can be traversed. That's fine. Yeah. Yes, so this is a like a diagrammatic illustration of the whole solution. So suppose on the left we have a street network. So the square is a depot. The circles are the nodes, not the meters, the nodes, and the lines are the edges. And just imagine a distribution of meters across the street network. I've not shown the meters, but the meters can be anywhere. And suppose a utility company manager has defined certain li values for various meters in this graph. So the stage 1 does this. So it chooses certain street segments that has to be traversed for meeting the likelihood levels of all the meters as pre-specified in the stage 1 IP. Now the stage 2, just so again, this is an NP-hard problem, so we cannot solve it optimally. So you have to like design heuristics for solving that. And suppose the heuristic solution gives us something like in picture C. But keep in mind that the RFID receiver of the vehicle is always on. So, but just by traversing the red street segments, we are done. We have like reached our LI levels of likelihood for reading each meter I. But while traversing the blue street segments, we are doing more than required. So can we trim down the routes and use a shorter route and still meet our likelihood levels? So after we get the initial solution in C, we see, okay, if there are ways, what is the route segment that is increasing the like that has the most marginal impact on the cost, and that's this red street segment. So if I remove this one, all these arcs are also gone, and I get a smaller route, and then I verify that whether I'm still kind of meeting my likelihood level of Li for each meter I, and then kind of this heuristic runs for certain time period and then stops with a feasible solution. It might not be optimal, but it's a feasible based on how much time limit you have provided to run the algorithm and the heuristics. Okay. Now this was the optimization part. Now so all this while we have assumed that we know the PIGs, the probability that meter I is read from street segment J at least once, but we have to learn that from the data. We don't know it. So suppose we know the PIJs, we solve the two-stage IP, stage 1, stage 2. So using that route, the vehicle will go out the next time it goes out for meter reading. It will collect more data. And supposedly we can update our learning about the PIJs, and this cycle can go on. So how do we learn about the PIJs? So the PIJs have to be estimated from the data. These are some variables that we can like easily extract out from the data. It's called variable selection, feature engineering, all sorts of fancy terms have come these days for machine learning, but basically these are the variable selections for any supervised learning method. So shortest distance IJ, shortest distance between meter I and street segment J, number of pulses J. So a number of pulses the vehicle can receive on street segment J. So if a vehicle is traveling faster, the number of pulses the vehicle can receive on street segment J will be lower, and vice versa. Number of customers I. So how many meters are there within a radius of 500 feet from a particular meter I? Because remember, I mentioned that if there are too many RFID sources, interference happens and the signals die out. Okay, so the shortest distance should have a like a inverse relation with the probability. The lower the shortest distance, the higher the probability. Number of pulses should have a like a like a directly proportional relation. More the pulses, more the probability of reading PIJ. And number of customers is also inverse relation. So if there are too many customers within a certain radius of 500 feet, the probability will be lower. So the dependent variable that we have is dichotomous. It's 1 or 0. 1 means that meter I has been read from street segment J at least once, and 0 otherwise. And so what we need is values between 0 and 1. So the probability is PIJ. And so given this setup, this is a classic situation to use a logit model or a probit model. Now we can live with logistic regression or probit regression. What is all the fuss about? Why do we have to use Bayesian updating? And the motivation is that every time the vehicle goes out, it collects more data. It adds to our data set. So the previous data doesn't get like so the previous information is also important, but we add to that information every time the vehicle goes out. So if you think about a regression, what will happen is, suppose you are doing a fresh start. You are a new company starting meter reading for the first time. So in time period 1, you have collected data Y1. So you run the regression on Y1 to learn the probabilities for generating the route for time period 2, in which you again accumulate data Y2. And so if you do the regression way, you have to kind of add, like put together all the data Y1, Y2. And so a lot of storage issues come that you have to keep appending to the huge data. And we saw that a 6-hour route from a city generated 337,000 read events. So it's not practically possible to store all the data and running the regression again and again on the ever growing data set. So that's where Bayesian updating comes. P theta is a prior. So again, so the first line is about time period 1. It's a fresh new company, or it's a new city being built. So you have no prior information. So P theta is the prior defined by the user. You have no prior information. So the idea is to generally use a vague prior. A vague prior is like a standard normal distribution with like very large tails. I should say normal distribution with 0 means and very large like variance, maybe 10,000 or something. So it's practically like a uniform distribution, but mathematically, structurally, it has a normal form. So a vague prior meaning that you know nothing about the situation that you are trying to assess, and you don't want to bias the situation by adding certain information to it by having a more proper distribution. So you just use a vague prior. And so L theta given Y1. So Y1 is the first data point accumulated on time period 1. So L theta is the likelihood. So that gives us the posterior. The posterior distribution becomes the prior for the next time period. So we don't have to store data. And the analysis is much faster because all the information from the older data set are stored in the forms of distributions, and you just kind of like do mathematical computations on the existing distribution, the existing prior, which is the posterior from the previous step, and the new incoming likelihood distributions based on the new incoming data. And also you can do all sorts of fancy things. Suppose you're doing a meter reading in the winters when the leaves are not there versus summers. So they're like in colder countries, the leaves fall out. So that has a huge impact where you have like too many trees and all, and those also creates hindrance. So you can accordingly weight the data, the priors distributions based on the seasonality, and do all sorts of fancy tuning to the computation. So, okay, that's the motivation about using Bayesian updating over regression. But we also have to do a proof of concept. How do we know that our choice of this fake prior works? Regression, we know that sure shot, it works correctly, it gives us a PIJ. But how do I know that this Bayesian updating really works in the practical setup? So I do have to do a proof of concept before kind of moving forward with that. Okay. So we use three different Bayesian updating models. The first two are just equivalent to the logistic regression and probit regression models. So I have the independent variables of shortest distance, number of pulses, number of customers. The logit model is basically log of odds. And the probit model is inverse CDF of the standard normal distribution. These are the dependent variables. The logit model assumes a logistic distribution, and the probit model assumes a normal distribution. The logistic distribution is little kind of flatter, so the tails are thicker. So logistic distributions are good at capturing more extreme values. However, in Bayesian updating, probit model, you can exactly compute the prior and posteriors, and you can do a Gibbs sampling. I will go in the slides, but basically there is a exact algorithm available for the probit model to kind of compute the posterior distribution, because you can mathematically exactly compute the means and the mean and the standard distribution and the standard deviations of the normal distribution. But for logit model, that's not possible because it's a logistic distribution, and you don't have a proper like a distribution available in the exponential family to kind of do for the computation to work out. And so there is a non-exact algorithm available which works just as good, called the Metropolis-Hastings algorithm, to compute all the parameters of the Bayesian updating model. And so the third model is a more like a designed model according to the problem. So I split the random variables into two levels. So the initial line is the lower level model. So basically, I'm trying to look at the interaction of the meter with the street segment. And the higher level model brings all the meters together and looks at their similarities or dissimilarities. So the model is split into kind of two parts. So in the logit and probit model, I just had 4 parameters to estimate: beta 1, beta 2, beta 3, and beta 4. However, in the hierarchical model, I have beta 1, beta 2, beta 3 for each meter I to estimate. And I'll also have the 6 higher level parameters to estimate. And with their error terms and all those things. So here is the proof of concept. So suppose it's day 1, it's a new company or it's a new city, you have no prior information. So you just kind of go out once, you get the data and you do regression and you estimate the beta parameters. And you do the same thing using the Bayesian updating way. The only thing is that in Bayesian updating for time period 1, you use a vague prior, as I mentioned. And you have to make sure that the parameters match nicely. So this is for the logit model. So as I was mentioning, the shortest distance have an inverse relation with probability. Number of pulses has a direct relation, and number of customers again has an inverse relation with probability. And that's how the parameters worked out. And if we look at the parameters estimated from the Bayesian updating way, the Metropolis-Hastings random walk algorithm, the parameters match very nicely, which means the proof of, and this is a proof of concept for the Bayesian updating method, that if I use a proper, like a correct vague prior, don't bias the computation, then Bayesian updating works just as well. And now these parameters are their underlying. So this is the mean values of the distributions. Now I have the distribution stored with me for beta 1, beta 2, beta 3, beta 4. Now I will just update those distributions with new incoming data in time period 2, and I will have new parameters for time period 3. The size of the data set was 5 million. So 6,000 meters were read, and the vehicle traveled on 829 street segments. So I times j, 5 million size. For the interest of time, I will kind of skip the details of the Metropolis Hastings algorithm, but it is basically a random walk. So you have a old beta and you walk to
I
a new.
think you have another 10 minutes or 15 minutes. So if you want, you can.
I have certain more slides to cover. Yeah, the like still ground to cover.
I see. Okay.
Yeah.
Okay.
Anyway, so overall, this is basically a random walk algorithm. You have an old beta and you choose a new beta with a certain probability. And then there are like the Hessian inverse and certain parameters that you have to do tuning. So these are called the hyperparameter tuning in any typical statistical learning or machine learning, whatever you may call. Now for the probit model, a similar proof of concept. Again, the shortest distance number of customers have a negative value for the parameters, and number of pulses is a positive value. Again, the data set is 5 million. And as I mentioned, the probit model has exact algorithm available, gives sampling. So again, the values match. And so this is also another proof of concept for the probit model too, that if I start with the correct wake prior, don't bias the computations, the results match. And so for the future time periods, I can move forward with the distributions obtained from the Bayesian updating and not like avoid doing regression. So this is the exact computation, the math, how it works out for the Gibbs sampling. So this was a heuristic, right? So you assume a multivariate normal distribution for the error, and then you just walk epsilon step from the old, and you accept the new or not based on a certain probability, and you keep repeating those steps 10,000 times. However, so for the probit model, this is the exact algorithm. So you start with a prior distribution. And this prior can be a vague prior. As I mentioned, the V0 can be very large number that will like practically make it a uniform distribution, even though the normal structure will still be there. So just remember that the dependent variable is 0 and 1. So dependent variable is not continuous, but for the math to work out, we have to choose a latent variable, which is basically a cover up for the binary dependent variable, and this latent variable is assumed to be continuous. So this latent variable has a normal distribution, and so basically it's an indicator. So this is the actual decision variable of the actual dependent variable binary 0 1. So all I'm saying is if my continuous latent variable is positive, this will become 1. If it's negative, this will become 0. And so this is a standard technique whenever the dependent variable is not a continuous variable and you want these equations to kind of work out, you have to always choose a hidden latent variable with certain assumptions. And so with this probability and with the likelihood function, this is the posterior that kind of mathematically works out. So this is the multivariate normal with this mean and this as the variance. And this is how you run the Gibbs sampling algorithm. So you start with a sample of y star given the other parameters, and you choose y star given beta, and you keep repeating that. And if you repeat it 10,000 times, you will get a kind of a statistical, like a kind of a numerical distribution with 10,000 runs, and that will kind of mimic the true distribution very nicely. Now, let's look into the hierarchical probit model and understand how it works. So this is also a probit model, not a logic-based model, but this is a kind of a tweak of the probit model. So the dependent variable is still the phi inverse of Pij. So it's still the inverse CDF of the standard normal distribution. So basically here I have beta 1, 2, 3 for each meter I to estimate. I also have to estimate the thetas, the deltas, and so these parameters, the thetas, deltas, are called the higher level parameters, and the beta i's 1, 2, 3 are called the lower level parameters. So practically, the higher level parameters don't have any meaning. But once we look at the lower level parameters that are computed based on the high level parameters, we'll see where this is going. So this is the distribution of beta 1 for all meter I. This is the distribution of beta 2 for all meter I, and this is the distribution of beta 3 for all meter I. So the takeaway message from this slide is, if we don't use a hierarchical model, if we just use a standard logit or probit model, we will be just using one value for all meter I. However, in reality, every meter is like, each meter is different, and they kind of take their own values when you give the model the opportunity to do so. So this is like a trade-off between too many parameters in the model, or like just kind of making your life easy. So here we see that just adding one level to the Bayesian updating setup, or the probability estimation setup, we see that every meter is different, and every meter gets its own values of the parameters, and this is a distribution of all those 8,000 meters. And if we just use a standard logit or probit, we will be just using one value, which will be kind of a weighted average of all these values for each of these parameters. And so the estimation should be better with a more granular model. But again, the computation time increases a lot with way too many parameters to estimate. And this is again the math to work out for the Gibbs sampling algorithm for the hierarchical probit model. So again, we have to define some prior distributions. This is the prior distribution for the lower level parameters, prior distribution for the theta, the high level parameters, and also for the error term. IW is inverse Wieser distribution. This is basically a multivariate gamma distribution. Then again, you have the latent variable that we need, because again, the yij's are again 0 and 1. So we need a continuous latent to cover up the mathematical equations. And then we have the posterior distribution for the lower level parameters after all the math, and then the posterior distributions for the high level parameters. Now using these distributions, so analytically we know the distributions, and now we can just run the Gibbs sampler. So choose yi star given yi and beta i's, choose beta I given all the other parameters, choose theta given others, and choose lambda given others, and you keep repeating these steps, and you get all the values of these three. All the beta i's, you get the theta, which is a matrix, and you also get the lambda, which is also a matrix. Yes, now let's again come back to the bigger picture that we kind of looked before. So now we know a way to update the probabilities if we have new information. Once we know the probabilities, we have a two-stage integer program to solve the to get the vehicle routes for next time. But this is not real world. I cannot really really go to the field. Well, I can, but it's time taking. So the ideal way of doing it is you actually wait for the utility company to give you the new data next time the vehicle does. But I chose to do it the simulation way. So basically, I can assume that whatever probabilities. So I have this huge data, like 37,000 read events from 6 hours of route. I like throw all the data into the algorithms, the Bayesian updating algorithm, and calculate the probabilities. And I assume that that's the true probability. And every time I try to simulate the real world scenario, I use a binomial distribution with that so-called perceived true probability Pij to kind of whether to like find out whether a meter has been read from a street segment J or not. If the outcome is 1, it has been read at least once. If the outcome is 0, it is missed. And the binomial distribution that I use, the binomial random variables probability, is basically Pij. And that Pij is the perceived true probability that I calculate from throwing all the data at once to the Bayesian updating model. And using that true probability, I run a simulation. So first period, I know nothing about the network, the meters, how they behave. I use a wake prior. I accumulate some data using the simulation. I update my prior distributions and get a new posterior, which is the prior for the next step. I run the IP again. Again, the vehicle goes out. It does some reading based on the simulation experiments. It accumulates more data. So this is the simulation setup. Um, if this is not very clear, the simulation setup, maybe this is a good time to ask questions. So all the data I was showing, all the parameter values that I was showing is perceived as the true values for the whole network, and that PIJ I used for my binomial like a coin toss. Well, not a like half and half, but a weighted coin toss. Any questions?
Okay, so is there any questions?
Okay, then if not, then I will move forward.
Yeah.
So
Yeah. Hey, Debdatta, I have one small question.
yes.
Maybe you finish the talk and then I can ask. Okay.
Okay.
Yeah, you can.
Okay. So that's the simulation setup. So this is the real world street network of Hartford, Connecticut. So all the red dots are the meters. So in optimization operations research, especially in the field of routing, there is a wide usage of artificially designed instances like street networks or various problem instances. So I'll just randomly assign some certain nodes and arcs and run my experiments on that. But since for this I had real data, I chose to run the simulation on real data, because in real world, the meters are not randomly scattered in a 2D space, rather they're clustered. Real houses are clustered on street network. So I wanted to capture the true effect on the actual street network of the city from which I got the data, which is Hartford, Connecticut. So these are the simulation results. So on the left hand side of the slides, the left hand side two charts as like have chosen the likelihood values LIs to be 0.75 for all meter I. The right hand side two charts have chosen a very high likelihood of 95% for all the meters I. The top two charts are for the route lengths varying across various iterations of the simulation. The bottom two charts are for the missed meters. And then we have 6,000 meters to read. The blue line is for the logit model, red is for the probit, green is for the hierarchical probit. Now we see that the hierarchical probit, remember that it has too many parameters to learn, and so it needs more data. So that's again a trade-off in any statistical learning between exploration and exploitation. So whenever there are too many parameters to learn, it needs more data to learn. There's no magic behind it. It needs more data. So always the algorithms kind of, they go into a exploration mode. They will kind of do something like get a solution that will give the algorithm more data so the parameters can be estimated properly. So we can see that the hierarchical probit model, like the route lengths are higher. So it's oscillating situation, because first iteration it chooses a very high route length, number of meters are lower. We can see it here below in the below plot. And then the next time it becomes confident, and so the route length decreases, and so it misses more meters. And so that way it kind of tries to reach equilibrium about the street segments that need to be traversed. So if we compare 0.75 with 0.95, all the three models have a higher route length because we are demanding more out of the problem. And similarly, all the three models have lower missed meters. Again, there's no magic. It's just the whole problem is about correctly learning the probabilities, and based on those probabilities, how can we choose the best streets to kind of do the job in the maximum in the minimum route length possible. So yeah, we can see that the logit and probit model like does pretty similarly, but the hierarchical probit has higher route length but lower missed meters. Now how do we say which is the winner? This is we are like driving more, albeit we do know now which street segments to drive on, but we are driving more, and we are missing less meters. So we have to kind of find a way to compare apples and oranges. So here is how we kind of compute, like bring those two parameters at scale and then compare. So in this RFID meter reading, the vehicles are actually driving very slowly at 5 miles per hour, because they're driving through neighborhood street segments, and they also know that if they drive fast, they will miss the number of pulses, independent variable, as I was mentioning. So a route of D1 miles take D1 by 5 hours to complete. This route will miss, say, M meters. And so another vehicle has to be sent to read those missed M meters. And so these M meters will be kind of read by a traditional VRP, not a CEVRP. And the reason is because you have already missed those meters. So you don't know that, is there some issue with the RFID tags? Has the batteries run out? So you don't want to take chances, because coming back again is way too more expensive. So you will kind of drive right in front of the meter. The driver will kind of step down and go and manually read the meter. So that's why it's a traditional VRP. Now this second VRP, the traditional VRP, to cover those M meters, will take D2 miles, and we can compute these values from our simulation experiments based on which meters have been missed in each iteration. And the vehicle will also drive faster, because now it's not dependent on the signal. Rather, a person will drive, park the vehicle, go out and manually read the meter. So you can drive, and generally the speed limits are of 15-20 miles per hour in the neighborhoods. So D2 by 15 hours. However, there is a time cost to step out, park the vehicle and manually read the meter, and let's assume it to be 5 minutes. So M by 12 hours to reread those meters manually. And so that's our equation. So D1 by 5 plus D2 by 15 plus M by 12. So in the simulation experiments, the route length that we were looking at was only D1, but we were kind of ignorant to the fact that there is a D2 and an M by 12 component to it. And so when we bring all that to the picture, let's see how everything works out. So the initial route, right? So initial route is just the deterministic CVERP. So deterministic meaning, the formulation I showed on the top right corner of the integer programming slide, that you just assume that if a certain street segment is within 500 feet of a meter, you read that meter. So it's a deterministic CEVRP. So that route is of 20 miles. It misses about 300 meters, 330 meters out of 6,000 meters. And then the D2 miles is like D2 route is 25 miles to read all these many meters, and this is the total route, about 33 hours. The Logiter Probit model at 0.75, well, the D2 is smaller, but they have more missed meters, and their total comes out to be 17 hours. For higher likelihood values, the D1 is way longer, 37 miles, but number of missed meters are lower. And so in total, we do better, 13 hours. However, for the hierarchical Probit model with 0.75, it's 28 miles, only 6 meters are missed. So the total hours is about 7 hours. And this very nicely also fits into a 1-day work schedule of a driver. And with a higher likelihood, the route is way too longer, and there's not too much value in reducing further missed meters, and so we do worse. And so this is another takeaway message from any machine learning statistical algorithm: hyperparameter tuning. One needs to be very careful while tuning the hyperparameters. We don't want to overdo parameter tuning so that it hurts our solutions in the end. So based on the model, we have to do proper tuning for each specific model types. Yeah, so this Bayesian updating actually helps us to kind of make our process of learning the probabilities faster. It makes it scalable. The simulation experiments show that the hierarchical probit model, if used correctly with the proper hyperparameters, has the most impact on improving the routes. And however, we see that we had about about, I think, 3,000 street segments in the whole network, but only 830 were traversed by the driver. And in vehicle routing, it happens that there are like localities where a particular driver goes every time, be it like delivery, be it Amazon package delivery. They have a designed locality because they are familiar with the street, so they're always assigned, and so they always love to travel the same streets every time. But that hurts the exploration phase of any learning algorithm, because we only have information about the streets. We have the real information about the streets in which the vehicles are actually traveling, but we are only estimating the probabilities from other streets in which the vehicle is not actually traveling. And so to learn the true stochasticity, there should be like a more exploration done by the utility companies to kind of serve their purpose in the long term. And it is called like Bayesian, like there's a thing called KL divergence. So that parameter kind of helps in this information theory learning with the Bayesian way. Yeah, that's where I will stop. Yeah. Thank you. Any questions? Anything?
Okay, so thank you, Debdatta, for this elaborate talk. So I have just one question, that in the beginning, you were talking about electric meters.
Mm-hmm.
And I can see that, I mean, when you have two houses and several houses, I mean, those meters are joined by wires, right? So that gives some sort of network or some sort of graph structure between your data sources. So is there any connection between the data and the underlying geometry of the graphs that connects, or the network that connects the meters?
That's a very good question. So what I can answer is that at least in the US, we are talking about residential meter reading. In residential meter reading, the houses are not connected by wires.
Okay.
In a commercial complex, they might be. However, what might be the meaning of that connection is that all the information from various different meters that are connected like among each other. Basically, if I have 10 meters in a click formation, then any meter will give me the information for all the 10 meters.
Right.
Probably that's the case, which means basically reading a particular meter among that click is as good as reading any other meter. So that will kind of change our stage one IP formulation, how we model that. So
Okay.
there will be OR condition. We have to like model it linearly to still keep it a linear IP and to make it faster, like fast solvable. We have to kind of think about constraints that take into this OR condition, that meter 1 or meter 2 or meter 3 or meter n, and at least like just one of them is just read at least once, and you are done. So if we model that OR condition into the stage 1 IP, it will capture that.
Okay. 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 So
Debdatta, I had a question about your large number of meters. So of course, there will be variability between the meters, but if it is accepted that they behave the same way over time, that means their behavior is stable over time, then it should be possible to group them and then form the data so that you can at least take that variability into account. Is that done? I mean,
so that's not done, but that is very much doable, and that is doable in the distributions of the Bayesian part. So there we can have like different distributions for a particular group of meters. But what happens is that batteries die out, weathers change, new meters are installed, a new construction goes, so that
you don't actually know that it's actually the same meter from the same location which is giving you the data necessarily. Same device.
It does, right? Because suppose if a new building is constructed between a particular street segment and the meter, or weathers change.
Meter will,
yeah,
right.
but yeah, you can certainly group, like you can not go into that detail, and you can certainly cluster meters and just kind of try to have one, like in the standard Logitech Probit model, I had one distribution for each meter.
The information bottleneck approach, you try to cluster somehow.
Sorry, please, your voice cut out.
I mean, that's the general idea, that you always try to reduce the number of variables by doing some
Exactly. So what you suggested is like a middle ground, not having the hierarchical model at its most general form, and neither having the standard form, rather grouping, like clustering meters and based on their properties and behaviors, and just having one distribution per cluster, and we might end up with maybe 20 clusters.
Right. Yeah. So that sounds like a
okay. Okay, so is there any more questions?
Yeah, I had a question.
Yeah.
It was a really nice talk. Thank you for that. So I had a comment and a question. So the comment was that you mentioned that PIJs, if they are close, you can talk about correlation, not the dependence. But it depends on, like you mentioned, it depends on the distance and also on the crowding effect and so on. So you may end up having a erroneous dependence there if you just look at the PIJ values, right?
So that's why the hierarchical model is there to save our day, because it is exactly designed for that purpose, that we are kind of trying to learn how each meter is unique on its own. However, we are just trying to capture how locally. So I have to say that I'm looking at the interaction like in a local level, like if there is a meter, how, like which are the other meters that are around me and how are they interacting. So if meter I is in the neighborhood of meter J, the vice versa is also true.
Right.
So
So locally, you that would give you some information, but
yes.
globally, if you look at, I mean, one PIJ being similar to another, which is
No, globally, yeah,
right,
as Professor Paranjape mentioned,
right.
the overall assumption is that it is independent in this product
Locally, it would
form.
give you something.
Yeah.
Yeah. The other question I wanted to ask, if there is an online, I mean, it would be much more difficult problem, but if you take into account traffic situation, because you mentioned food delivery where it's an online optimization problem, right?
Yes.
And since you are optimizing over time in terms of time for best route, so do they take into account the traffic situation and do some kind
No,
of
this
online?
particular data set, I didn't have traffic information, but one can use a Google Map API to kind of at least have a average time to it, which will, so mathematically the problem stays the same, but what that will do is that will add another parameter. So you
Right.
can think of it as C superscript T subscript J. So basically based on the time, the cost of traversing street segment J changes. And that CTJ in the easiest of scenarios will be like a average of say last 5 days or last week or last 4 Mondays. If I'm doing it on a Monday, last 4 Mondays, and so just increase the variable. So but mathematically the approach and everything will remain the same, just adding more like parameters to the model. And accordingly the decision variable will not be just xj, rather that will be also xtj.
Right. Okay, one last thing. Why do you have only one vehicle? Why is
So I'm looking at a so in vehicle routing, always there are two approaches of doing routing, and at the end you end up with just one vehicle for a certain portion of the network. So it is called route first, cluster second approach. So basically the heuristics, the way it works is you just assume one vehicle, you do the full routing, and then you use heuristics to cluster it out, and each cluster gets assigned to one vehicle. Or you kind of first form the clusters and then route them, and then keep tuning that like iteratively in like various 2-opt, 3-opt approaches, various other kinds of approaches, simulated annealing, various approaches.
Okay, thanks.
So if you have multiple vehicles, suppose you're not solving this problem, you're actually solving that, okay, fine, these are multiple vehicles. Objectives vary. Objectives vary in the sense that what do you want to achieve? Do you want to minimize the total route length across all the vehicles? Then that will be just another summation, like a double summation across the other vehicles. But many times when it's a time sensitive job and I'm sending 10 different vehicles in 10 different like sub networks to kind of do their job delivery, metering anytime, and it matters is when the last vehicle ends. So then it is like a min max approach. I'm basically minimizing the worst case scenario, the worst, the slowest vehicle or the last incoming vehicle.
Yeah, I was just wondering that if you are deciding the route online, then it's a problem if you have more than one vehicle, because then they should not traverse the same road. But okay, that's not what you're doing in. Okay, thanks.
Any other questions?
Okay, so I don't know. Thanks for the talk anyway. Yeah, nice talk. It was very informative.
Yeah. Okay.
Thank you. Thanks for the
Okay.
invitation, and yeah, this is a nice initiative.
Okay, Debdatta, so thank you very much for this
Thank you.
wonderful talk, and it was great to see you after a long time.
Yeah.
Yeah. So I'm very happy that you came here for giving this talk. I hope you will visit here in person sometime.
Yes.
Yeah,
Next time I'm
and
in India, I will
yeah, we
surely.
can have coffee together. Yeah. Okay.
Thank you.
Okay.
Bye.
Bye. Have a nice time ahead. Okay.
Bye. Thanks for
Okay.
coming.
Okay.
Thank you.
Bye.
Bye.
Bye.